In this segment, we're going to continue with a few more tools from discrete probability, and I want to remind everyone that if you want to read more about this, there's more information in this Wikibooks article that is linked over here. So first, let's do a quick recap of where we are. We said that discrete probability is always defined over a finite set, which we're going to denote by U. And typically for us, U is going to be the set of all n-bit binary strings, which we denote by 0, 1 to the n. Now, a probability distribution P over this universe U is basically a function that assigns to every element in the universe a weight in the interval 0 to 1, such that if we sum the weight of all these elements, the sum basically sums up to 1. Now, we said that a subset of the universe is what's called an event, and we said that the probability of an event is basically the sum of all the weights of the elements in the event, and we said that the probability of an event is some real number in the interval 0 to 1. And I want to remind everyone that basically the probability of the entire universe is basically 1 by the fact that the sum of all the weights sums up to 1. Then we defined what a random variable is. Formally, a random variable is a function from the universe to some other set, but the thing that I want you to remember is that the random variable takes values in some set V, and in fact, a random variable defines a distribution on this set V. So the next concept we need is what's called independence, and I'm going to very briefly define this. If you want to read more about independence, please go ahead and look at the Wikibooks article. But essentially, we say that two events A and B are independent of one another if, when you know that event A happens, that tells you nothing about whether event B actually happened or not. Formally, the way we define independence is to say that the probability of A and B, namely that both events happen, is actually equal to the probability of event A times the probability of event B. So multiplication, in some sense, the fact that probabilities multiply under conjunction, captures the fact that these events are independent. And as I said, if you want to read more about that, please take a look at the background material. Now, the same thing can be said for random variables. So suppose we have two random variables, x and y, they take values in some set V. Then we say that these random variables are independent if the probability that x is equal to A and y is equal to B is equal to the product of these two probabilities. Basically, what this means is even if you know that x is equal to A, that tells you nothing about the value of y. Okay, that's what this multiplication means. And again, this needs to hold for all A and B in the space of values of these random variables. So just again, to jog your memory, if you've seen this before, a very quick example. Suppose we look at the set of 2-bit strings, so 0, 0, 0, 1, 1, 0, and 1, 1. And suppose we choose a random element from this set. Okay, so we randomly choose one of these 4 elements with equal probability. Now let's define two random variables. X is going to be the least significant bit that was generated, and y is going to be the most significant bit that's generated. So I claim that these random variables, x and y, are independent of one another. And the way to see that intuitively is to realize that choosing R uniformly from the set of 4 elements is basically the same as flipping a coin, an unbiased coin, twice. The first bit corresponds to the outcome of the first flip, and the second bit corresponds to the outcome of the second flip. And of course, there are 4 possible outcomes. All 4 outcomes are equally likely, which is why we get the uniform distribution over 2-bit strings. Now, variables x and y, why are they independent? Basically, if I tell you the result of the first flip, namely I tell you the least significant bit of R, so I tell you how the first coin, whether it fell on its head or fell on its tail, that tells you nothing about the result of the second flip. Which is why intuitively you might expect these random variables to be independent of one another. But formally, we would have to prove that for all 0, 1 pairs, the probability of x equals 0 and y equals 0, x equals 1, y equals 1, and so on, these probabilities multiply. Let's just do it for one of these pairs. So let's look at the probability that x is equal to 0 and y is equal to 0. Well, you see that the probability that x is equal to 0 and y is equal to 0 is basically the probability that R is equal to 0, 0. And what's the probability that R is equal to 0, 0? Well, by the uniform distribution, that's basically equal to 1/4. That's 1 over the size of the set, which is 1/4 in this case. And well, lo and behold, that's in fact, these probabilities multiply because, again, the probability that x is equal to 0, the probability that the least significant bit of R is equal to 0, this probability is exactly 1/2, because there are exactly 2 elements that have their least significant bit equal to 0. 2 out of 4 elements gives you a probability of 1/2. And similarly, the probability that y is equal to 0 is also 1/2. So in fact, the probabilities multiply. Okay, so that's this concept of independence. And the reason I wanted to show you that is because we're going to look at an important property of XOR that we're going to use again and again. So before we talk about XOR, let me just do a very quick review of what XOR is. So of course, XOR of 2 bits means the addition of those bits modulo 2. So just to kind of make sure everybody's on the same page, if we have 2 bits, so 0, 0, 0, 1, 1, 0, and 1, 1, their XOR, the truth table of the XOR, is basically just the addition modulo 2. You can see 1 plus 1 is equal to 2, modulo 2, that's equal to 0. So this is the truth table for the XOR, and I'm always going to denote XOR by this circle with a plus inside. And then when I want to apply XOR to bit strings, I apply the addition modulo 2 operation bitwise. So for example, the XOR of these 2 strings would be 1, 1, 0, and I guess I'll let you fill out the rest of the XORs just to make sure we're all on the same page. So of course it comes out to 1, 1, 0, 1. Now we're going to be doing a lot of XORing in this class. In fact, there's a classical joke that the only thing cryptographers know how to do is just XOR things together. But I want to explain to you why we see XOR so frequently in cryptography. Basically, XOR has a very important property, and the property is the following. Suppose we have a random variable y that's distributed arbitrarily over 0, 1 to the n. So we know nothing about the distribution of y. But now suppose we have an independent random variable that happens to be uniformly distributed also over 0, 1 to the n. So it's very important that x is uniform and that it's independent of y. So now let's define the random variable, which is the XOR of x and y. Then I claim that no matter what distribution y started with, this z is always going to be a uniform random variable. So in other words, if I take an arbitrarily malicious distribution and I XOR it with an independent uniform random variable, what I end up with is a uniform random variable. Okay, and this is again kind of a key property that makes XOR very useful for crypto. So this is actually a very simple fact to prove. Let's just go ahead and do it. Let's just prove it for 1 bit, so for n equals 1. Okay, so the way we'll do it is we'll basically write out the probability distributions for the various random variables. So let's see, for the random variable y, well, the random variable can be either 0 or 1. And let's say that P0 is the probability that it's equal to 0, and P1 is the probability that it's equal to 1. Okay, so that's one of our tables. Similarly, we're going to have a table for the variable x. Well, the variable x is much easier. That's a uniform random variable. So the probability that it's equal to 0 is exactly 1/2. Probability that it's equal to 1 is also exactly 1/2. Now let's write out the probabilities for the joint distribution. In other words, let's see what the probability is for the various joint values of y and x. In other words, how likely is it that y is 0 and x is 0, y is 0 and x is 1, y is 1 and x is 0, and 1, 1. Well, so what we do is basically, because we assume the variables are independent, all we have to do is multiply the probabilities. So the probability that y is equal to 0 is P0. Probability that x is equal to 0 is 1/2. So the probability that we get 0, 0 is exactly P0 over 2. Similarly, for 0, 1, we'll get P0 over 2. For 1, 0, we'll get P1 over 2. And for 1, 1, again, the probability that y is equal to 1 and x is equal to 1, well, that's P1 times the probability that x is equal to 1, which is 1/2. So it's P1 over 2. Okay, so those are the 4 probabilities for the various options for x and y. So now let's analyze what is the probability that z is equal to 0. Well, the probability that z is equal to 0 is basically the same as the probability that, let's write it this way, xy is equal to 0, 0, or xy is equal to 1, 1. Those are the 2 possible cases that z is equal to 0 because z is the XOR of x and y. Now these events are disjoint, so this expression can simply be written as the sum of the 2 expressions given above. So basically it's the probability that xy is equal to 0, 0 plus the probability that xy is equal to 1, 1. So now we can simply look up these probabilities in our table. So the probability that xy is equal to 0, 0 is simply P0 over 2. And the probability that xy is equal to 1, 1 is simply P1 over 2. So we get P0 over 2 plus P1 over 2. But what do we know about P0 and P1? Well, it's a probability distribution, therefore P0 plus P1 must equal 1, and therefore this fraction here must equal to a half. P0 plus P1 is equal to 1, so therefore the sum of these two terms must equal a half. And we're done. Basically, we proved that the probability that z is equal to 0 is 1/2. Therefore, the probability that z is equal to 1 is also 1/2. Therefore, z is a uniform random variable. So this simple theorem is the main reason why XOR is so useful in cryptography. The last thing I want to show you about discrete probability is what's called the birthday paradox. And I'm going to do it really fast here because we're going to come back later on and talk about this in more detail. So the birthday paradox says the following. Suppose I choose n random variables in our universe U. Okay, and it just so happens that these variables are independent of one another. They actually don't have to be uniform. All we need to assume is that they're distributed in the same way. The most important property, though, is that they're independent of one another. So the theorem says that if you choose roughly the square root of the size of U elements, we're kind of ignoring this 1.2 here. It doesn't really matter. But if you choose square root of the size of U elements, then basically there's a good chance that there are two elements that are the same. In other words, if you sample about square root of U times, then it's likely that two of your samples will be equal to one another. And by the way, I should point out that this inverted E just means exists. So there exists indices I and j such that Ri is equal to Rj. So here's a concrete example that we'll actually see many, many times. So suppose our universe consists of all strings of length 128 bits. So the size of U is gigantic. It's actually 2 to the 128. It's a very, very large set. But it so happens that if you sample, say, around 2 to the 64 times from the set, this is about the square root of U, then it's very likely that two of your sample messages will actually be the same. So why is this called the birthday paradox? Well, traditionally it's described in terms of people's birthdays, so you would think that each one of these samples would be someone's birthday. And so the question is, how many people need to get together so that there are two people that have the same birthday? So just as a simple calculation, you can see there are 365 days in the year, so you would need about 1.2 times the square root of 365 people until the probability that two of them have the same birthday is more than a half. This, if I'm not mistaken, is about 24, which means that if 24 random people get together in a room, it's very likely that two of them will actually have the same birthday. This is why it's called a paradox, because 24 supposedly is a smaller number than you would expect. Interestingly, people's birthdays are not actually uniform across all 365 days in the year. There's actually a bias towards September, but I guess that's not relevant to the discussion here. The last thing I wanted to do is just show you the birthday paradox a bit more concretely. So suppose we have a universe of about 1 million samples. Then you can see that when we sample roughly 1,200 times, the probability that we sample the same element twice is roughly a half. But the probability of sampling the same number twice actually converges very quickly to 1. You can see that if we sample about 2,200 items, then the probability that two of those items are the same already is 90%. And, at 3,000, it's basically 1. So this converges very quickly to 1 as soon as you go beyond the square root of the size of the universe. So we're going to come back and study the birthday paradox in more detail later on, but I just for now wanted you to know what it is. So that's the end of this segment, and then in the next segment, we'll start with our first example encryption systems.